Alright, ladies and gentlemen, this class recording has started. So, I will preface today's class recording with this. This outline that we're going to do today is not real long, so if we're focused and we can get through it, and you guys have a little bit of time at the end of class to work on what you might need to work on. There's a little homework tonight, and I'll explain that when we get there. But let's stay focused, let's finish up this work, and then we'll deal with that when the time comes. Okay. All right. So today's unit, or today's lesson, starts the unit on forces and Newton's laws. But let's backtrack just a little bit, and let's just talk about the unit that we just completed on mechanics. We said mechanics is studying what? Motion. Okay? And we talked about the 4 questions that we wanted to answer to describe our motion, right? So we want to know, where is the object? What is it doing now? What's it going to do next? And when? Okay? When are all these things happening? So there's actually 2 more W questions that we talked about, right? The 5 W questions. We've got where, and we've got what, and we've got when, but we're missing 2 W questions. Who is just whatever is doing this, but then the last question is why? Why do all of these things happen? And the answer to that question is force. Force is the reason why all of these things happen. Okay? So force answers the question of why. So let's talk about what force is. Okay? Force is another one of those terms that I'm sure you've heard of before and that you've probably used before. If I said, hey, what's a force, you might tell me it's a what? If you had to demonstrate a force, what might you do? Not the force necessarily, but a force, okay? What could we do to demonstrate a force? Any ideas?
Pick something up.
Pick something up, right? Or what else could you do with the thing that you've picked up? You could throw it or push it, right? Okay? And that's what forces are, right? Forces is a push or a pull on an object. So forces are a push or a pull. And that's great. But remember that we're looking to answer why. Why does this motion happen? And the reason is force. Because forces are pushes or pulls, but we're not really interested in what forces are necessarily, but what they do. And forces cause acceleration. Forces cause acceleration. And based on our knowledge from last unit, what is acceleration? Slowing down, speeding up, or changing direction. Or we can talk about more formally a change in velocity or a change in what is happening, right? So that means forces can cause objects to speed up or slow down or change directions or do one or more than one of those things at the same time. You can speed up and change directions. You can slow down and change directions. It's kind of hard to speed up and slow down at the same time. Okay? But forces cause all of those things to happen. Forces are the cause of acceleration. Forces cause things to change what they are doing. Okay? Good there? All right. Forces are vector quantities. And we learned in the last section that a vector quantity means that what does force have to tell us? Magnitude and direction. So in the case of a force, what does the magnitude of the force tell you? How much that's acceleration. How much we change is acceleration, right? What's the first thing you wrote down on force? Push or a pull. So the magnitude of that force is how much you push or pull, right? But then the direction is which way am I pushing or pulling, right? How big is the force, or how much do we actually push or pull? And then which way is that force acting? The combination of what an object is doing now and what force is applied to it will tell you what happens next. it will tell you the acceleration. So forces cause acceleration. Forces are vector quantities. Okay? For instance, if I have this book sitting on the table, right? See if that works. I have this book sitting on the table, okay? Right now, we would say its velocity is what? 0, okay? If I push it towards your left, what's going to happen to this book? It's going to, instead of saying it's going to move to the left, what is actually going to happen to it as it moves to the left? What is it doing now? What is its velocity? 0. If I push it, it's going to accelerate. Specifically, what kind of acceleration? Okay, it's going to speed up, right? Okay, so it's going to speed up in that direction. Okay, but let's say that somebody else pushed the book towards me. So it's already moving to your right. Yes? And then I put my hand out like this. There's still a force in that direction to your left, right? But now, because the book was moving to the right, what happens to it? It stops. It slows down. So the same force in the same direction might cause an object to speed up if it was already sitting still, or it might cause an object to slow down if it was like moving towards you. Does that make sense? Right? So that's important with the magnitude and direction, because we could have the force in the same direction and the same magnitude, but it could do different things depending on what that book is already doing. Does that make sense? You get that? It still causes acceleration, but it can cause a different kind of acceleration depending on what the original motion already is. Okay? To represent the vector nature of force, we use arrows. It's convenient because the arrow points in which way the direction the force is acting. And then we try to make the length of the arrow represent the magnitude of the force, especially if there are more than one force acting on it, if there is more than one force acting on an object. For example, there's book sitting on the table. What's its velocity? 0. What's its acceleration? 0. It's not moving, and it's continuing to not move. Is there any force on that book? Okay. We know that gravity acts on things all the time. So just because this book isn't moving doesn't mean that gravity isn't acting on it. But what else is acting on that book? The table, right? Which way is the table going to push on this book? Upward, right? What would be the magnitude of the table's force compared to gravity? The same, right? Because in the end, if one was pushing harder than the other one, what would happen to this book? It'd go in that direction, okay? So here, with the two forces, they might have the same magnitude, but they would be in the opposite direction. And we could represent that on a picture with two different arrows. Okay? Good there? All right, so that's what force is. Causing acceleration. Okay. How do forces work? Well, there's two ways that forces can do their thing, can make acceleration occur. The first is called a contact force. And like its name suggests, there's going to be some physical contact between objects, right? These are your pushes and your pulls and your friction and things like that. Contact forces. There have to be things that are in contact in order to cause the acceleration. However, just spent a big amount of time talking about gravity and the effect of gravity, right? And we talked about how gravity will slow this ball down if we throw it in the air, and it will speed it up if we drop it. Those are accelerations. And it can also cause things to change direction. If we think about the moon as it orbits the Earth. If the moon goes in a circular path, is it accelerating? Are circular paths acceleration? Yeah, because they keep changing direction. So gravity can cause things to slow down, speed up, or change direction. But when I drop this ball, does anything reach up and grab it and pull it to the ground? At least nothing apparent, right? So there is another way that these things can work, or these forces can work, and we call them field forces. Field forces can change the motion of an object without actually touching it. The one that we deal with probably most often is gravity, but you're probably familiar with those other ones that we threw up there, right? Things like magnets. Magnets can cause other magnets to accelerate, even though they don't actually touch each other. Okay? Same thing with positive and negative charges. We know that positive and negative charges attract each other, but they would attract each other even if they don't touch each other, right? If we do the whole balloon on the head trick, right? We rub the balloon, right, on the head, but then we can make your hair, if you have hair, you can make your hair move, right? Even though it may not actually touch the balloon. Sometimes it actually does, but sometimes it doesn't have to. Or have you guys remember the stations that we did around the room when we were doing the electrostatic stuff? You took the rubber rod and you rubbed it with rabbit fur, and then you put it by the water that was streaming out of the faucet, and it makes the water move, even though it doesn't actually touch. Those are field forces, changing the motion of an object without actually touching it. All right? So, and we also talked a little bit about a force field, right? I didn't put force field on there. You might want to just make a note on the side about force field, right? We talked about this when we were talking about electric charges. There's an electric field, the area that surrounds a charge where it can affect other objects. Okay? A force field is an area that surrounds an object where it can affect other objects. And now we know that affecting other objects, we have a fancy name for that, it's called applying a force. That it can cause other objects to accelerate, even though there's no contact. We live in the gravitational field of the Earth. Earth's gravity affects this object, even though it doesn't touch anything. The Earth exists in the gravitational field of the sun, because the sun's gravity causes the Earth to go in its orbit, right? It causes the Earth to accelerate. So the field is the area that surrounds an object where it can affect other things. Okay? Good there. All right. So, forgot this part. Field strength, or how much it can affect the motion of another object, or how much it accelerates another object, depends on how far away you are from that object. The field strength, or its ability to accelerate other things, decreases as we get farther and farther away from an object. Okay? The planet formerly known as Pluto, right? Or the object formerly known as the planet Pluto, if you want to think about it that way, right? Okay. Doesn't experience as much gravity from the sun as we experience from the sun because we're much closer to it, right? Pluto is farther out in the sun's gravitational field, so it doesn't experience as much gravity. Okay? Good there? All right. So, measuring force. How much force are we actually applying? Okay? we use the SI unit of the Newton. If you can't figure out where it gets its name from, just wait till tomorrow and I'll tell you. Okay? So, we use the capital letter N to represent newtons. It's a measure of how much force is being applied. But how do we define a newton? Well, here's our long-winded explanation. 1 newton is the force required to cause an acceleration of 1 meter per second squared on a 1 kilogram object. 1 newton is the force required to cause an acceleration of 1 meter per second squared on a 1 kilogram object. Okay? Good there? So let's take a look at a picture. Okay? So here's a picture of a little hockey puck on a little hoverboard, like an air hockey table. Okay? So because the air is pushing up on the hockey puck, right? It gets rid of the friction that exists between the hockey puck and the table. So all we have to worry about is my hand. Okay? So 1 kilogram is this force. The hockey puck was back here to begin with. Then we applied a force. If it was sitting still, and then we apply a force, it's going to start to move. That's acceleration. Okay? So, if we take this hockey puck over the course of 1 second from a velocity of 0 to a velocity of 1, that's 1 newton worth of force. Okay? That makes sense how we sort of define it. Okay? So, newton, like I said, is a derived unit. Okay? And that means that it's a combination of base units. Okay? So, when we talk about 1 newton, that's the equivalent of 1 kilogram. Oh, actually, write it this way. 1 kilogram for 1 meter per second squared. Okay? That makes sense? And we summarize all of this together like this. Okay? That's actually fine. Sorry, everybody. I got a little too ambitious. 1 kilogram, 1 meter per second squared, and that all gets summarized into this big complex fraction. So whenever we write the capital letter N, we're using that as a shorthand way of representing this big combination of units. Okay? It's a derived unit. It has, in order to measure force, we have to measure mass and acceleration, and that requires multiple measurements. Okay? Good there? So when we have a newton, just keep in mind that that actually is being a combination of those base units to show what's actually happening. Okay? Good there? All right. We learned a little earlier that there are 2 ways that force can do its thing. One, we can have a contact force where this guy is physically pushing this box, right? I mean, this guy too, look at him. He's a hoss, all right? How do I know he's a hoss? Because he wears a hard hat. Look at that. And look at how much back force he's applying to that box. 4 lines worth of back force. That is unheard of. So, right? But more importantly, contact force, actual physical contact. Whereas here, this guy cliff diving, right, will accelerate on the way down because of gravity, but that's field force, right? So this is sort of how forces do their thing. But what we find out is that there are, 3 or 4 types of forces that exist out there. All right? So the first we call electromagnetic forces. Electromagnetic forces exist between what two things? Remember we learned that electricity and magnetism are kind of the same thing, sort of, right? What actual objects are exerting forces on each other when we're talking about electromagnetic forces? What do we say electricity depends on? Electricity. And I know it's all the way back like before Christmas break. Oh, gosh. Electricity comes from where? Electricity. Charges, and what are charges? There are two things that are charged that we know of, right? What are they? Protons and electrons, right? So electromagnetic forces are the forces that exist between charged particles, positive and or negative charges. And we learned, right, that positive charges come from what? Something that has a positive charge has more what than what? Protons than electrons. Something that has a negative charge has more electrons than protons, right? That's how it gets its negative charge, okay? Electromagnetic forces are weird because they can actually work in two directions. We can have an electromagnetic force that attracts if we have opposite charges, right? But we can also have electromagnetic forces that repel each other, that push away. And that's if we have like charges. So electromagnetic forces are weird in the sense that they can sometimes attract things together, but also they can push things apart, depending on what the charges are like. Okay? Keep that in mind, because that's one thing that makes electromagnetic forces different than the other forces. Good there? And this is the case when we have like protons and electrons and magnets, right? And we did a whole bunch of examples of these kind of things, how they can affect the movement of other charged particles when we did our stations lab and all the things we talked about with electric motors and all that kind of fun stuff. That all works on the basis of electromagnetic forces. All right, good there? Yes, no, maybe? Okay, that's one kind of force. There's another kind of force called the strong nuclear force. Strong nuclear force. Based on its name, what do you think the strong nuclear force acts on? The nucleus. Specifically, what part of the nucleus? Oh, now we have to go back and remember what's in the nucleus of an atom. Oh, gosh. So, what's in the nucleus of an atom? Protons and neutrons. What do we think the strong nuclear force acts on? The protons or the neutrons? Do neutrons do anything to each other? They're neutrally charged. They just sit there. But we learned, what do protons want to do to each other? They want to repel, right? So the nucleus of an atom shouldn't exist. We shouldn't have these positive charges that are just sitting there next to each other. But we do. Why? Because we have something to hold them in place. The strong nuclear force is an attractive force that holds the protons in the nucleus of an atom together. And we have evidence to suggest that neutrons help with the proton holding together. That's why neutrons are there, to sort of hold those protons together. There is one isotope. Ooh, there's a hard word from a long time ago, right? Isotope. There is one isotope that doesn't have any neutrons. It's hydrogen, or hydrogen 1. Hydrogen 1 has 1 proton and 0 neutrons. How come there's no neutrons in hydrogen 1? Well, what do neutrons do? Well, yeah, neutrons don't repel each other. That was a good one. What repels each other, I guess? Not neutrons, but protons. Electrons will too, but protons do, right? But if hydrogen 1 only has 1 proton, is there anything to repel? No. Nothing to repel. Doesn't need any neutrons. Okay? Good there? Now, here's the trick. The strong nuclear force is actually very strong. It can apply a lot of force, but it doesn't act over a very big distance. The strong nuclear force only acts on the nucleus. Once you get outside of the nucleus, it doesn't do anything. It's too weak to feel. So it doesn't affect electrons because electrons aren't in the nucleus. Right? When we talk about, steam shovels or rocket ships that send, big heavy objects into space, we have to apply a lot of force, but it's not the strong nuclear force. That only acts on atoms. Okay? Good there. You okay with that? The last type of force that we deal with, and probably the one you're most familiar with, is, let's skip that, gravity. All right? So, gravity does what to objects? Pulls them together. So we would classify gravity as an attractive force. Gravity is an attractive force between any two objects that have mass that exist in the universe. We're familiar with Earth's gravity acting on this ball, pulling it towards the ground, or slowing it down and then bringing it back to Earth, right? But gravity exists between any two objects that have mass. So while this object is going up and coming back down under the influence of Earth's gravity, there's also gravity between me and the ball. There's also gravity between you and your pencil. But the strength of that gravity depends on a couple of things. Right? Gravity, let's skip through this one here. Okay. The greater the mass of the objects, the more gravitational force there is between them. So the reason why it appears that this ball goes straight up and comes straight back down and doesn't get pulled towards me or to you or to these tables is because the gravity of Earth is very strong because it has a lot of mass. Okay? But if we take mass into account, Earth's mass is actually pretty small compared to the mass of other things out there, like the sun. You can fit 1,000 objects the size of Earth into the sun. Like, that's how much bigger the sun is than the Earth. 1,000 Earths could fit inside the sun if we could. Okay? But there's another thing that affects the amount of gravity, and that's distance. As we get farther and farther away from something, the gravitational force decreases. So, pop quiz. All right? What kind of relationship exists between gravity and mass? What kind of mathematical relationship exists between gravity and mass? Nope. Mass, right? What happens to the gravity as the mass gets bigger? Gravity gets bigger. So if one gets bigger and the other one gets bigger, what do we call that? A direct relationship. Yes. Okay. But then, when you look at the bottom one, right, as distance gets bigger, what happens to the gravity? It gets smaller. So what kind of relationship is that? That's an inverse relationship. Right? One gets bigger, the other one gets smaller. So one last thing on gravity. When we look at how gravity compares to the other type of forces, like electromagnetic and the strong nuclear force, gravity is much weaker than either one of those. Think about it. You take the balloon and you rub it on your head, you stick it to the ceiling. Those protons and electrons that you changed with the balloon are enough to hold that balloon to the ceiling, even though all of the gravity of the Earth is trying to pull it down. And it still can't. So gravity is actually a very weak force. But it acts over very, very large distances, like, I don't know, the solar system, or even beyond that. Okay? Hey, easy. We got to the end of the outline, but I'm not done yet. And you still have like 12 minutes left. You'll have enough time to pack your bag up. Don't worry. Okay. So, gravity, even though we think about it as affecting everything we do, and that's true, in the grand scheme of things, it's really not that big of a deal. Other than that it can affect over long distances, and that makes it very important in terms of the way we live, but also how the universe works. Orbits and things like that. Okay? Good? All right. Tomorrow, we will introduce Newton's first law and Newton's second law, and maybe help you get out of trouble for sleeping in too much on Saturday or Sunday. I'll give you an excuse that you can use. You can try it on your mom, see how it works. Okay. There is some reading and a little bit of homework on the calendar for tonight if you want to check it out. Just some basic stuff about force and what it does. Okay?